So we will start after 1 minute. Okay, so let's get started. And first, let me start with an announcement. There is a homework assignment 1 is out. So you will be able to find it in the KLMS as well as in the GitHub course webpage. And then the due, you are given about 2 weeks. And right, and just as I said before, also I wrote it in the problem sheet. I mean, if you please don't copy answers from your friends or any other sources. If a student is found to do the cheating, the students will get F automatically. Okay, so just solve those exercises for yourself. Okay, so we will continue our discussions on the domain theory and the semantics of simple imperative language. So here's a quick reminder about where we are. So let's like this. So last time we are in the middle of studying a simple imperative language. And then when I said the syntax and the intended semantics of the language is pretty obvious because that's the kind of language that you have used many, many times in typical programming languages before. But to give us semantics of this language, we need to do a little bit more work. That's because the semantics of while requires existence of fixed point, which means that we have to, in a sense, if we just use the set and functions, we can't really give the semantics of this language. So there comes so-called domain theory. And I said one way to understand domain theory is approximate computability theory. So we are not really talking about computability in the sense of a Turing machine, but we are talking about imposing some specific restriction to functions between sets that mirrors what can be written by program. Especially this domain theory, according to the textbook, try to formalize the limit of communication that happens during the computation. By communication, I mean communication between input and output, and then from the users to the input and so on. And more technically in the domain theory, we learn about something called posets, which is a set together with a partial order. And then we learn about so-called predomain. There is a poset. Typically in predomain, we use P. There is a poset where every chain has the least fixed point. and not list fixed point, list upper bound. That I will write it LUB. And then we talk about domain, which is a particular kind of a pre-domain which has the list element. So in this case, we use D to talk about the list element bottom. And this LUB is written as this square cup sign. I mean, that the list upper bound is denoted like this. And one important thing that we learn about this domain theory is we learn about something called continuous function. We actually learn about something called monotone function. So if you have a function f that goes from pre-domain P to pre-domain P prime, and we say the function f is monotone if we preserve the order. And also we learn about f when f is continuous, certain monotone function is continuous if it preserves the limit of every chain. And then we also said if it happens that P and P prime are domain, we say function f is strict if it preserves the bottom. Okay, so these are the three concepts that we learned. And then I said that continuous functions play a very important role because of the least fixed point theorem. And this is the theorem that we're going to use when we give the denotational semantics of the imperative language, simple imperative language we studied before. And the least fixed point theorem says the following. It says that if you have a domain D, so we are given a domain, and then if we are given functions from D to D, that is continuous. It doesn't have to be strict, but it has to be continuous. So if that's the case, then the theorem said f has the least fixed point. So what does this mean? This means that the least fixed is a least fixed point x in D. What does it mean that this x should be a fixed point? So it had to satisfy f of x is equal to x. So applying f doesn't change x. So that's what we mean by fixed point. And it has to be list. So this means that for any fixed point y in D, if it is a fixed point, then x is smaller than or equal to y. So it's a fixed, x is the fixed point, and among the fixed point, x is the smallest. Okay? That always exists in the domain theory. So that's what the least fixed point theorem say. And in fact, if you look at the proof of least fixed point theorem, it tells us what x actually look like. It say x is actually the least upper bound of particular chain that we can create by starting with bottom, which exists. That's because in the domain, if we apply function f once, we get f of bottom, twice f square of bottom, and so on. And that's gonna create, that will form a chain. If you take the least upper bound, that's, the proof of the theorem said that's going to be the least fixed point. Okay. So that's what we learned before. Then now we will study a little bit more. So the first thing I want to look at is to get some intuitions about continuity. Okay, so let's think about some function f that goes from one pre-domain. Let's just write it this way. We are given two pre-domains, P and P prime. And then suppose we have a function f that goes from P to P prime. And we can assume that this is monotone. And monotonicity, somehow you can understand this because it just means that you preserve the order. Okay, and this less than, I said, it's an approximation order, which means that this less than, in a sense, describe how computation will evolve and produce more and more values into the output. So this less than is an approximation order, and that means that you have preserved function f preserved the approximation order, means function f is monotone. Now, but one thing that's not quite clear is what continuity means. Formally, we know that continuity means that preserve the least upper bound of a chain, but here are just some intuitions about continuity, which say that intuitively f is continuous. For monotone functions, f is continuous if and only if, in order to produce a finite amount of information in the output, f uses only a finite amount of information in the input. Now, if you think about the f as a program, okay? Now, imagine a program that runs forever. So it takes infinite sequence or stream as an input. It produces stream as an output. That kind of program exists, like operating system is one example, that it takes an infinite stream as an input, infinite stream as an output. Now, if a program, if you take finite prefix of the output, then I say, okay, how much information of the input is used? Program can only use a finite amount of information in the input. Another example is that, I don't think any of you are working on exact real number computations, but suppose I want to produce okay, let's not worry about this. So, okay, so if it's an infinite stream, so f maps infinite, so say A, B, C, D, it takes infinite stream and it produces maybe some Korean letters. Then if you take finite prefix of the outputs and said, okay, how much input is used to produce this finite prefix? If f is a program, it can only look at some finite prefix. Because computation should happen in finite amount of time. So that's what this statement is telling us informally. But so here are just some concrete result that I want you to prove to see that's really the case. So let's think about two pre-domain, which is actually both of them are domain. I think I wrote it as like this. Star and omega. So in this pre-domain, each elements here are sequence of integers. So -2, -3 is a sequence of length 2, -3 sequence of length 1, but it can contain infinite sequence as well. So it's a Z star, which means finite sequence, and omega means infinite sequence. So it's a sequence, finite or infinite sequences of integers less than, f can be constant function. That's not a problem. So you're right. By less than, I mean less than or equal. So constant function is automatically monotone. It's monotone, it's just say, right, that's it, yeah. So constant function is a monotone function. So this is a one pre-domain. Another pre-domain is the power set. So if a set of natural numbers, order is a subset relationship. So in this case, this power set have some elements are like 2, 4, 5, and so on. And you can also have an infinite set, and subset is the order. Now think about some function f from that takes element in G star and omega and returns to the Z. So suppose that's a monotone. Now here's something that I want you to prove. So here's an exercise. Show that if f is continuous, actually this is if and only if, but just prove this, then it satisfies the following property. What the property say? The property said for all inputs for any sequence S in finite or infinite sequence and Z star and omega. Okay, and for all finite subsets A, this is a finite subset. So A is finite and Fs. So what does this mean? This means that we take an input and we apply F to the input. So this is going to be an output. Now for the output, we take only finite subset. We are not taking infinite subset, we are taking finite subset. That is a bit like taking finite amount of information in the output. So this finiteness is really important. So then there exists a finite subsequence of finite prefix of S such that, let's call it S prime, such that this A is still in F of S prime. Okay. Now, one thing I want you to notice is because the function F is monotone, if you take a finite prefix of S, apply function F, because if S prime is a finite prefix, this order relationship is true. So this is notes. So we know that F of S prime is a subset of F of S. Okay. But what this result tells us is that for if you only care about finite subset, finite amount of information in the output, you can always find finite amount of information. In other words, finite prefix of S such that it covers that information in the output, information A in the output. Okay, so that's the exercise I want you to try. Try to prove this. Okay, so I will give you 3 minutes to do so. Okay, let me tell you how to do this. Here's an answer. So to solve this exercise, let's consider, assume that f is continuous. And then also pick an arbitrary sequence S in G star omega and finite subsets of the output. Okay, so, and then if S is finite, then there's nothing to be done. So we can just set S prime to be equal to S, because the finite prefix doesn't have to be strictly smaller. S itself is a prefix of S. S itself is a prefix of S. We just have to make sure the prefix is finite, but S is finite, so we are done. Otherwise, which means that the sequence is infinite. So S will have the form like this: x0, x1, x2, x3, and so on. It's an infinite sequence for integers x0, x1 in integers. So in that case, we create a chain in G star X. So chain, and then the chain looks like this. It's initially empty. The next element in the chain, so let's call this is like S0, that's an empty. S1 that is contain x0. S2 that contains x0 and x1 and so on. So if we create a chain like this, then if it's take a list of bounds, list of bounds of Sn is equal to S, right? Because if you take, this sequence gets larger and larger. If you want to have some sequence which contains all of these as a prefix, that has to be same as S. Furthermore, we know that each of these xn is finite by construction. Okay, so now we use the continuity. So since f is continuous, f of s is the same as the f of, this is not yet we are using continuity. Because of continuity, we can take this list of bound out. In the case of, because the output is a set, this is going to be f of Sn. Okay. Now, what we know is that A is a finite subset. A is a finite subset of union n of f of Sn. Okay. And then furthermore, we know that like f of Sn smaller than f of Sn, because f is Sn plus 1. Because f is monotone. Okay, so what does this mean? This means that we have increasingly larger and larger sets, and their union will contain finite set A. That means that at some point, this entire A should be contained, because A is finite. So there exists some M such that A will be included in union n, which is 0 to m f of Sn. It's a bit detailed proof, and that is the same as f of Sn because of this monotonicity. Okay, so what does this tell us? This tells us this Sn is now what we are looking for, is a finite prefix. of S. And then it also satisfies the required property, which is that it contains the chosen finite set A. Okay, so that's how we can complete the proof. And more generally, this kind of phenomenon happens if we study what the Dana Scott originally did for the domain theory, which is a so-called algebraic CPO, or algebra, and there is some notion of finiteness, which is captured by compact element and so on. So this phenomenon happens in the most of the domains that we are dealing with in the semantics of programming languages. But I mean, to do it properly, we have to do a bit more, go a bit deeper into the domain theory, which we don't want to do it at this point. Okay, so I hope this can give you some intuitions about what's really happening. And now we move on to the next topic, which is, so we just covered the intuitions about the continuity. Continuity means to produce a finite amount of information in the output, we need to consume, the function will consume a finite amount of information in the input. Now, there are two important constructions that we're going to use over and over again in the domain theory. For predomains. Okay, so what these constructions do is that it's a bit like an operator that takes predomain and produces a new predomain. So the first construction is, so let's say we have the first construction is a function space. Actually, maybe three. The function space construction assumes that we have a predomain P and P prime. And we want to construct a predomain out of continuous functions from P to P prime. So this function space construction produces new predomain P double prime, then less than double prime, where P double prime looks like this. P double prime consists of continuous functions from P prime. So this is a notation which, instead of P double prime, I often use this notation. This means that the set of continuous functions from P to P prime, and then this less than order is going to be so-called pointwise order. So what does this means? This means that given two f and g, which are in P double prime, which are really continuous functions from P to P prime, we say f is less than g if and only if for x, g of x, for x in the domain. For every input, if f of x is smaller than equal to g of x, then we say f is less than equal to g here. Okay, so it's defined by applying functions to every input. So this is typically called pointwise definition. And perhaps, I mean, if you learn about linear algebra or some other things before, I mean, this kind of thing happens a lot. You just use what's available for the output, like a less than order for the output. And then you use it to define something for the functions. For instance, if you have take all the linear functions, if you want to construct a vector space out of linear functions, and you just use the plus operations for the output. Now, this is the kind of typical trick that people do, and that's also what we are using in the domain theory. And it happens that if you do so, okay, so this means that we defined the underlying set, we define some relation. So this is a relation. Then you may ask, is this form some nice relation, and it turns out that's the case. The one theorem said if you put P prime and this pointwise order, I will just write it less than often without double prime. P double prime is a predomain. So in other words, this less than double prime, this order for functions is a partial order. It's a reflexive, transitive, and anti-symmetric. So this is a partial order. Also for every chain has a list upper bound. Maybe has the list upper bound. So I'm not going to prove this theorem, but I will just show you what this list upper bound actually look like. So this list upper bound say that if you have a chain here, I use this sequence notation. If I have a chain, it's a chain from P to P prime, then its a list upper bound is defined pointwise. So the list upper bound of the chain is the following function. It takes input x, and which is in P, and it produces an output in P prime, and then the output is defined by applying each of this fn to x, so that's leaps in P prime. Then take a list upper bound in P prime. So that's a list upper bound in P prime. So in other words, this function itself is defined in a sense pointwise using informations or some stuff that's available in the output. And that's how the list upper bound is defined in this case. Okay. So it's not really a proof, but it's sort of the key idea behind the proof. And this space is really important. We're gonna use it in defining the semantics of the while language, the imperative language, simple imperative language that we are dealing with. Also, if we will also use domain theory to provide the interpretations of semantics for the functional languages, which provide the much more powerful applications and function abstraction mechanism. There, this space also plays a very important role. And now there are a few other some simple facts. So here's the first fact. The first fact is that when we set some set S together with discrete order. So this means discrete order. So x is less than equal to x precisely when they are the same. If we have this set and discrete order, so then every functions, and this is also can be understood as a predomain. And in this set together with the discrete order, the continuous function space from S to some predomain P prime that is identical to just set of all the functions from S to P prime. So in other words, if source doesn't have any interesting order relationship at all, two inputs have a less than equal relationship precisely when they are equal. So in that case, this continuous function will be identical to just set of all the normal function space. Okay. So we're gonna use this fact many times. And then also what this suggests is that in a sense, the continuous function is a generalization of the typical function space. The space of continuous functions can be understood as a generalization of the appropriate function space, the typical function, space of typical functions. Okay, so then, and the second, and if P target P prime is a domain, in other words, it contains the list elements, bottom prime. So then this function's continuous function space from P to P prime is also a domain. It's not just a pre-domain, but it's also a domain. Then this condition of the domain means that we should have a list element, and the list element is quite simple. What's the list element? The list element is, it takes X as any inputs, and it just returns the smallest element in the output domain. Okay, so that's the list element, and I'm gonna sometimes write this using the lambda notations, which take X as an input and produce the smallest element X prime as the output. So, I mean, just to sum up about the first construction, actually it turned out to be 2 instead of 3, because the function space consists of all the continuous functions. Order is defined pointwise. If we do so, this becomes a pre-domain where the list upper bound is defined pointwise. And then also the target space is a domain. Then it also becomes a domain where the list element is again defined essentially pointwise using information available from the target. Okay, that's the first construction, function space construction. The second, okay, so there's, before going to the second, here's some important result. Now, what is the, yeah, so maybe it's another theorem. So suppose we have a domain. Then by the least fixed point theorem, we can think about some map, which is typically written as a Y. That's a mapping that takes continuous functions on D and returns some element in D. But what does it do? If we take function F, it returns the least fixed point of F, which is defined by the list upper bound of this specific chain that we can construct using F. So the theorem say that this Y is continuous. So Y is an operator that takes a function as an input and produces an element in the output. And it turns out this Y itself is a continuous function. So in some programming language, everything that you can define are continuous in the sense of domain theory. That programming language have some operators like Y. And that is in a sense okay. That's because this operator Y, which take a function and return the fixed point, that operator is also a continuous function. It, in a sense, type check in this domain theoretic framework. Okay. So the proof is an exercise. So in fact, this exercise was a homework in the previous year, but I excluded it. But I strongly encourage you to solve this exercise. Okay, so that was the second construction. The second construction is lifting. And this construction is also pretty simple. So what's the given thing in this case? We have a given pre-domain P. And the purpose of this construction is to produce a domain as an output. Domain should using the given pre-domain. Okay. Now, how to do the lifting? So this lifting is written as like this, P bottom. So that's the output of the lifting operator or lifting construction applied to the given pre-domain P. So that's this lifting construction. And the definition is really simple. It's P bottom. Let's call it prime here. So P bottom consists of P together with some new element bottom. So we are assuming this is a new element, not in P. Okay. And then we say the bottom is the smallest element in P bottom. So for any x and y in P bottom, we said that x is less than equal to y in this new lifted domain. If and only if x is bottom, so x is the smallest element, then that's less than equal to anything in this domain, or x and y are both in P and they are already in less than relationship. So in other words, if in terms of a picture, if you draw this P as picture may not make sense to you that much, but I think the best one is to see an example. So typical example is just here's a set of integers together with a discrete order, which means that these integers are not ordered at all, like -3, -2, -1, 0, 1, 2, 3, and so on. And there are, so in this setting, some integer is less than equal to the other integers precisely when they are equal. Now, if you apply the z bottom, and then put an order that corresponds to putting some smaller element bottom, and then puts all the things above. So you can see why this one is called lifting. It lifts all the available elements by one step in some sense. Okay, that's why this is called lifting operator. And then simple fact that you can check is that this P bottom and this less than prime is a domain. And why this is the case? And the smallest element is something that we just added, is bottom just added. And okay. And then for the list upper bounds of a chain can be essentially computed using the list upper bound in P, okay? Because in any list upper bound whose any chain whose list upper bound is not in the chain should be essentially the chain in P. So if you just take the list upper bound in P, that's going to form the list upper bound in P lifted. So this is going to be a domain. And it's very simple, but it's quite important. So there are a few other important things that we want us to know. The first thing is called unit operation. And John Reynolds called it like I up arrow, but in other languages it's sometimes called unit. And this I up arrow in this case is a mapping that takes P and return P bottom, P lifted. And its definition is what you expect. I up arrow A is just return A. Okay, so it's embedding from P to P bottom. So for instance, this is a set of integers and then lifted integers. The I up arrow just take an element like -3 and just return it -3. So you can think of this as a type changing operator. And then the second operator is called Kleisli composition and Kleisli lifting. Actually, it's Kleisli extension. So this operator works like this. Suppose we have an element F that goes from P to P prime bottom. Okay, so where we have a P prime is another predomain. So then what we want to do, we want to define an operator, which is in the John's book, he wrote it like F, this is strange signed. And then this operator mapped from P bottom to P double prime bottom. And the definition is what you expect. We take element input X. And if input X is equal to bottom, then it will return bottom prime of the targets. So that comes from here. Otherwise, X should be in P. So in that case, we just apply X there. So both of them are changing. The first one embed this P to P bottom. The second one, change this map so that this map can work for every element in P bottom. And now here's something that I tell you. If my explanation make you confused, just ignore it. But I hope that at least to some of you, the explanation may be useful. So this P bottom, is the P bottom. Let me not explain this. This requires the notion of monad and so on. So let's not talk about this. So instead, let me just mention one thing. So why these two guys are important? If you have something like F and I bottom, okay, we can define some strange composition operator. Okay. So suppose we have a function F, continuous function. So this is a continuous function. And this I is also a continuous function that goes from P to P prime bottom, and G, P prime to P double prime bottom. Both of them are continuous. And we want to somehow compose these two things together. And actually we can do it if we use a Kleisli extension. So here's a very strange operator, composition operator, which composes F and G, and that can be done by lift F using Kleisli extension, and then compose it with G. This is normal function composition. It turns out if you do so, in this new guy, this is composition prime, that behave very much like a composition. What does this mean? This means that this prime is associative, and it also has a unit. By unit, I mean in a sense, identity elements. Just like identity function serves as an identity element for the function composition. What this associativity means that if you have one more k that goes from P double prime to P triple prime bottom. So then this relationship is true, K prime G F the same as. So this is like a function, the associativity for function composition. And then it also has a units. So if you have F, then I lifting. So this is for I lifting for P prime. And that's the same as F. And that also same as F lifting. This is lifting for P. So this is very similar to the identity function, is the identity element for function composition. And because of these properties are true, this is called a monad. And in a functional language, certain functional languages like Haskell, and actually provide language constructs that allows you to express something is a monad. And then this being monad is quite important because it means that we can use it to describe the computation very naturally. Okay, so the second of, yes, there's one more thing. The third operation is, maybe you can just say pure lifting. The first one is closely lifting, pure lifting. In this case, if we have a function f, that continuous function that goes from P to P prime, we write it like f bottom that takes P bottom to P prime bottom. And the definition is very similar to the one before. Say if x is equal to bottom, it returns bottom in the targets. Otherwise, it's just f of x. And strictly speaking, we have to put embedding here. But I'm often gonna omit this embedding. So the things are very, very similar as before. So this closely lifting and then just usual lifting, both of them are very, very similar, except the function that we are given, the targets in the second case is just P prime, not a lifted P prime. But the target that we are given in the first case is a lifted version. And in all these cases, we are using continuous functions. Okay, so that's the, in a sense, the quick review of the domain theory. So we talk about the pre-domain, domain, continuous functions, least fixed point theorems, some intuition behind the continuous functions, and these two constructions. One is construction of function space. The other is this lifting construction. And then the lifting constructions, the purpose is to make pre-domain into a domain. Maybe just write some simple lemma, which is a very simple fact, which is that P bottom less than is a domain. So I already wrote it over there, I guess. Yeah. Okay. So that's the quick review of domain theory. And then now let's use it to define the semantics. Of the simple imperative language. So the semantics is going to be defined by, in a syntax directed way. And so it's going to be what I call a denotational semantics. So actually, there's actually one very important principle in the denotational semantics. When you define the denotational semantics, the most important part of the denotational semantics to identify what kind of space you are using to interpret commands and integer expressions and so on. Often, if you kind of spell it out, what space that you are using, that actually captures many of the important design decisions in the programming language. And once you get used to it, to the denotational semantics, the actual interpretation of a command follows automatically. So what do I mean by interpretation of, say, types, or the use of the space? I mean, that means the following. So in this case, types correspond to non-terminals in our abstract grammar. So what are the non-terminals we have? We have a non-terminal, one is called integer expression. Second, we have, I think, the Boolean expression. Well, what we used. Yeah, so it's a Boolean expression. The third non-terminal was a command. So the important bit is to specify what kind of space we're going to use to interpret integer expression, what space we're going to use to interpret Boolean expression, what about the commands. Okay. So here's what we're going to do in this particular language. In this particular language, we're going to use this interpretation functions, which is called integer expression. Sometimes we're going to omit this subscript and also interpretation function for Boolean expression commands. So these underlying subscripts will be omitted often. So the first guy will take integer expression and it will return something. Okay, so by specifying space, I mean identifying what should be the target space. That's actually quite important part. I mean, the most important part of the semantics of denotational. I mean, that is the process of giving denotational semantics. So what's going to be? In this case, it's going to be a mapping from states to integers. So where the sigma is a set of all the functions from variable to integers. Okay, and then for Boolean expressions, it's going to be mapping from state to Boolean. For commands, it's going to be mapping from commands to mapping that takes input state and output state, but it will be lifted. Okay, so I mean, as I said before, if the source space is set, okay, and the set of, if you view each of these set as discretely ordered pre-domain, the set of continuous functions and the set of functions are exactly the same. Okay, so you can view this, put a subscript C here, or you can omit this. It doesn't really matter. So both of them can be understood as a continuous functions. So in the same way, the sigma integer Z, Boolean B, they are all discretely ordered. And then this sigma bottom, that's the only one which have a non-trivial order. It has a bottom, smallest element, and all the rest are discretely ordered. Okay, so in this, so that's the shape of the interpretation. And then this shape actually tells quite a bit about what kind of things we are assuming for this particular programming language. The first, so what are the things that's expressed in this shape of the semantics? The first thing is that integer. So this bottom often express non-termination or sometimes error stop. Okay, but now if you look at this semantics, you can see that the outputs of these targets in the semantics of integer expression is just normal integer or Boolean. It doesn't have any bottom. What does this mean? This means that first, evaluation of all integer and Boolean expressions terminate and without an error. So that's the assumptions that's expressed in this denotational semantics. And then the second of some things that you can see from here is that now for this, because the commands can return a bottom, that means commands may go on forever. So it doesn't, sometimes program may fall into an infinite loop. So that's the second thing that's expressed in this domain. The third thing is that now you might say, because my program has an integer expression and Boolean expressions, maybe in some programming languages, variables may store integer values and Boolean values and so on. But this language is different. In this language, we are saying the state is always a mapping from variable to integers. So that expresses another decision that we make in the design of this programming language. The third decision is that all variables store only integers. Okay. So sometimes, people say there are denotable values and storable values. So in this language, we can denote Booleans and integers using expressions, but only integers can be stored. So these are the kind of decisions that expressed in this language. Now, based on these decisions, we can now express its semantics in the syntax-directed way. So for integer expressions, this is an integer expression. This is the same as before. So if you provide a state sigma, that's essentially the same definition that you see before. And Boolean expression, this is again same as before when we talk about the semantics of predicate logic. So we are not going to talk about this. Also, if you want, you can reconstruct these definitions very, very easily. Just syntax-directed definition, just simple kind of inductive definition. If it hits the base case, which are variables, that's the time when we use this state to look up the value. Now, the interesting bit in this specific case is the interpretation of a command. That is not something that we did before. So because it's a syntax-directed definitions, we give us case analysis. So there are skip case, and then there is assignment case. And a sequential composition case. And then if then else. And then while loop. So I will give you 3 minutes to fill in the details here. So what should be returned in all these cases? It should be the targets in all these cases should be sigma lifted with sigma bottom, lifted sigma. So it can be either states or bottom. So try to write a definition in all of these cases. And the last bit, if you don't know what's really going on, it's going to be hard. But if you understand what's going on, typically the first 4 cases are very easy. The last case is not that easy, or requires more thinking. In this case, try to use least fixed point theorem. Or the operator Y that I explained to you. Operator Y for domain D is that it takes continuous functions, and then it returns the least fixed point that is also again continuous. And this, if you try to use this this sometimes called Y combinator or fixed point operator, you can give a semantics of Y. We'll give you 3 minutes, and then I will tell you the answers. Okay, so let me tell you how you can solve this. Just erase all this. Okay, the first 4 cases are quite easy. So if you for skip shouldn't do anything. So if you're given input state sigma, the output state should be identical to sigma. For assignment, given state sigma, what you have to do is we have to update the value of variable x with the value of expression e. So the output state is a sigma, where the variable x is now bound to the new value, which is the value of expression e. Now for sequential composition, we can use this lifting operator that we defined before. So we first run C1, sigma. So then this output may be either some states or maybe bottom. Okay. On the other hand, if you look at the semantics of C2, and then we have to run C1 first and then run C2 next. But if you look at the semantics of C2, that's going to be a mapping from sigma to sigma bottom. So we have to make sure C2, when you run C2 for the output of running C1, what we are running should be prepared for the possibility of non-terminations. So if the C1 sigma is equal to bottom, we should be able to run it. So we're gonna use this Kleisli lifting that we talked about. In this case, it's going to be a C bottom to sigma bottom. And then we will apply it here. Computationally, what does it mean? It means that when you run C1, if the first program does not terminate, the entire thing is not going to terminate. So that's why first program not terminating gets reflected as the output is equal to bottom. So if the input to C2 is equal to bottom, that's the entire thing is going to be bottom. Otherwise, so if C1 terminates, we're gonna just run C2. Okay, that's what's expressed by this definition. And then the third one is essentially if then else means if then else. So here, this if then else is from the syntax. I mean, this is from the English. So if B sigma is equal to true, so if that's the case, then we run the output state or bottom is going to be determined by execution of C1. Otherwise, it's going to be determined by execution of C2. And this is what you expect. If then else means if then else. So here, this if then else here means English, but this means syntax. The most difficult part is this while. And I will tell you what it means now, and then maybe we're going to talk about it again on Wednesday. So the semantics of a while is going to be determined by applying this fixed point operator to sigma bottom. I said this is also, I mean, you can put C or not C, it doesn't matter because the source space is discretely ordered, but this is a function space. And then this function space is also pre-domain. But furthermore, because this target is contains bottom, it's going to be a domain. Okay, so it's going to be a domain. And so we can apply this Y operator. So instead of D here, we are plugging in this function space, sigma bottom here. And then we will define some operator F. And that operator will have, what does it do? It's going to be a bit more complex. It will take continuous functions and then return another continuous function. If we do so if you apply Y to F, that's output is going to be some element in D, which is in this case, the sigma to sigma bottom. So we apply this Y operator to F and then apply sigma here. Okay. So now what's going to be F? So F will define like this. It will take, so this actually is also continuous, define small f, and then some input state sigma prime. And then it does essentially an onward version of this while loop by once. So if you check the Boolean conditions of the while loop with input given sigma prime, if this is equal to true, so then do something, and else it does something. But if this Boolean condition is equal to false, okay, that corresponds to getting out of the loop, so without doing anything. So it could just return I prime. If the Boolean condition is equal to true, that means we have to run C once, the body of the loop once. So that's C is same as body. We run the body of the loop once, and then we run the rest of the loop, which this F captures what's going to happen after the one iteration of the loop. So we will run this closely lifting of this F to the result here. So intuitively, this F represents the loop after one unrolling. F can be anything, okay? But in intended usage of this capital F, small f means loop after, small f represents the loop after one unrolling. Of y. And then the sigma prime is an input state. So this capital F expresses what's happening in the loop in a bit onward manner, in a bit more general manner. And then so that we can apply this fixed point operator, y operator to F, that will give us the meaning of these while loops. And then so that we can now apply the entire thing to the input state sigma. Okay, so that's it for today. And I will talk a bit more about this while loop. And there are several issues that we have to think about. The first issue is, okay, where is this definition actually coming from? So in other words, why we have to define while loop as a fixed point? So why of this particular F? So that's one question. A bit more difficult question is, why least fixed point? So why we have to use a least fixed point? And we're gonna talk about these on Wednesday. And then we'll finish off this section in this chapter on the simple imperative language. Okay, so that's it for today. And if you have any questions, you can ask me. I'll be around here for about 5 minutes.